A network covalent solid is a giant macromolecule that is connected with covalent bonds. They have the highest melting points of any substance. They are insoluble in water. They are poor conductors but good insulators, and they are super strong. Some examples are diamond and sand or silicon dioxide. It's also known as quartz. That's more the crystalline form. You can melt down sand and make glass. That would be an amorphous form. The crystalline form, that would be the form that we would call a network covalent solid. If you look at a diamond, why is a diamond so hard? And it's because each carbon is covalently bonded to four other carbons. So it's basically making a tetrahedral shape all throughout the whole molecule. So for diamond, each carbon is sp3 hybridized, connecting it to four other carbons. It gives it a whole bunch of tetrahedrals put together. Because it's sp3 hybridized, it gives it that super strong strength that is reflected in its melting point. A different form of carbon is called graphite. So instead of having carbon form tetrahedrals, it actually forms these little hexagons, and there's some double bonds in there. And you have these really strong sheets of a network solid, but in between the sheets you have dispersion forces. So it's dispersion forces that are holding the sheets together. But each sheet is super strong. Graphite is found in your pencil. So as you write with your pencil, you're putting force and smearing these sheets across your paper. You are essentially breaking the dispersion forces. That is how you write with a pencil. If you look at graphite and its hybridization, it's sp2 hybridization. This is showing that pi bonding. Remember, pi bonding, it is not a hybridized bond. Instead, it's a bond that's based on the p orbitals being on the right plane. So you are going to get on these sheets, these electrons are going to be moving around and around the molecule, and this helps with the hardness. You can also take carbon and make a Buckminster fullerene, which is this spherical structure, and you do have double bonds in there, so every carbon, it does have four bonds. These are affectionately known as buckyballs. They have been able to use these as lubricants, and they have thought of doing tiny experiments inside the Buckminster fullerene, but most of the emphasis in the research has been on nanotubes. So these also have some double bonds in there. Every carbon is bonded to four other carbons. It is sp2 hybridized, so not as strong as the sp3 of the diamond. And these are all allotropes of carbon. One more allotrope to talk about, and that is graphene. So with our electronics industry, scientists are very interested with graphene. This is a single graphite layer, and this single graphite layer is super strong. It can also conduct a current. Those nanotubes could also conduct a current too. But between the nanotubes and the graphene, the research as far as something that conducts a current and is super strong. And with the graphene, they've shown that you can wad it up and then flatten it out and it will still carry a current. And so people are thinking of the electronics industry and using graphene.